Welcome to video on two-stage opamp. This is a second part of two-stage opamp circuits. So in the previous video we discussed about a two-stage opamp consisting of a differential amplifier followed by a CS amplifier. So the differential amplifier has got a gain of has got an output voltage of V0 dash, and the final output voltage of the two-stage opamp was V0 from the CS amplifier. So we have assumed that R1 dash C1 dash are the output resistance and output capacitance of stage 1, and R2 dash and C2 and R2 are the output capacitance and output resistance of second stage. And it was also seen that the Bode plot of two-stage op-amp was given by has got two poles at frequency P1 dash and P2 dash. So we have minus 20 dB corresponds to first pole and minus 40 dB corresponding to second pole, and this is the gain crossover frequency where it is crossing 0 dB, and we have the phase margin happens to be very small. So this is what is phase margin, and here we are plotting minus of A beta, that's why it is 180 and 0 degree. So we already discussed about this in the previous video. So you can see now the phase margin is very small. So that is at this point at omega GC, the corresponding phase is almost less than 10 degrees. Now we know that if the phase margin is very small, we're going to have the more amount of overshoot, which will have a larger settling time. Settling time will be more if the value of phase margin is small. So we need to have from this graph, which is an indication of settling time and the phase margin. If the phase margin is more and more, then the settling time is less. So it is now necessary to increase the phase margin so as to reduce the settling time. So for that we need to go for compensating the two-stage op-amp. So next we are supposed to learn how to do the compensation for two-stage op-amp. So now as it was discussed, the phase margin is less, so zeta is less, so naturally the settling time is more. In order to reduce settling time, we are supposed to increase zeta. So in order to increase zeta, we are supposed to increase the phase margin by compensation technique. So one of the compensation technique is the Miller's compensation. So Miller compensation is nothing but having a capacitor CC between the output node and the input of that second stage op-amp, that is a CS amplifier. So we are connecting a CC. Now this is called as compensating capacitor, that's why the suffix CC. So it's a capacitor for compensation, that's why it is CC, and we call this as a Miller compensation because Miller is an effective capacitance between the output and the input. So it is final output and the input of the CS amplifier. So let us know the effect of Miller compensation, which we already discussed. The effect of Miller compensation is that the poles which were there at P1 dash will move towards P1. The pole which was there before compensation, which was at P2 dash, will now move to P2. So because this P1 dash and P2 dash are poles on the left hand side without the Miller capacitance. Now we didn't had any zeros there. Now upon putting the compensation capacitor CC, which is not equal to 0, this P1 dash has moved close towards the imaginary axis. Now it is P1 here. Now this is the new location of P1 dash, and P2 dash has moved more towards the left side of the S plane, and the zero which was the two zeros which were there at infinity, so one of the zero will become finite. I can see now this is one of the zero of two finite zeros which were there when there was no compensation capacitor. So because of that compensation capacitor, out of two zeros at infinity, one has come to a finite value, other one is still at infinity. So let us try to see the effect of this Miller compensation and the Bode plot. Now you can see the dotted line corresponds to the uncompensated frequency response, the magnitude plot, here this was omega P1, this was omega P1 dash and P2 dash. So we had first cutoff frequency, second cutoff frequency. Upon providing the compensation, so the gain bandwidth, the omega GC remains constant, but this omega P1 dash, which was here, now it has been reduced here, now it has been moved here, and this, which was omega P2 dash, has been moved towards the right side. This has moved towards the left side. The omega P1 dash has moved towards the left side, that is corresponding to P1 dash has moved to P1, the P2 dash has moved to P2 now. So because of this movement of the poles, naturally the phase margin, you can see now, just have a look at this one. The earlier one was the solid, the dotted line is the earlier phase plot without compensation. Now we can see we didn't had no phase margin, so the phase margin was almost 0 here because of this dotted line. This is your GB, that is omega GC. Now you can see this is the compensated phase plot. Now you can see we have this is the intersection of omega GC on the phase plot. Now we have this is the phase margin. Now the phase margin has now increased. Now we have this much phase margin. Earlier we didn't had any phase margin. So this is the effect of having a Miller compensation. By putting a Miller compensation, we effectively move the poles uh, from their original position of P1 dash and P2 dash to P1 and P2, which ultimately makes our the phase margin more. Let us try to understand the same movement of the poles P1, P2, okay, how they are moving and how does the 0 will be coming into existence. So this is the two-stage opamp with Miller compensation. So this is that capacitor which is used for used to provide the compensation so as to increase the phase margin of two-stage opamp circuit. Now you can see this is the equivalent circuit of this two-stage op-amp circuit with the compensation. You can see it is similar to that of the earlier without compensation. Only thing is that of course we have this GM1 dash GM1 V in as the current source corresponding to the first stage, and we have R1 C1, which is the output and output impedance, output resistance, and the output capacitance of stage 1, and we are having similarly for second stage output resistance and output capacitance. And see here, this CC which is there between the output and the input of your second stage has been put here. Now this is that compensation capacitor. So let us consider node A and node B here. So we will write the KCL at node A and node B. So at node A, so we know that we have currents living. Let us assume the currents living as GM into V in, that is this current, and we have the voltage over here as V0 dash. Corresponding to that, the current through R1 is this, and the current through C1 is this current, and we have the current flowing through CC, which is the potential difference across that divided by the impedance. So this is what is the currents living node A. So these are the current livings node A, that is 1, 2, 3, 4. That is, we have one current, second, third, and the fourth current. So by rearranging the terms containing V in, V0 dash, and V0, we can actually write the expression for V0 dash as equal to given by this particular expression. So let us name it as equation number 1. Similarly, we write it for at node B, we'll write the KCL. So at node B also we have current due to this current source GM into V0 dash, which is one current, plus one more current which is flowing here. Let me just now, here I am directly writing it as it's actually V0 divided by R2. So 1 over R2 is now written as G2 here, and plus this is one more current through capacitor, which is now V0 divided by the capacitance of this, which is 1 over V0 divided by 1 over SC2, so which can be written as V0 into SC2. So similarly we have the current through CC, which is the potential difference of V0 minus of V0 dash divided by the impedance of capacitance. So this we can rearrange and write it as this expression. V0 can be written as this and V0 dash can be written as this. Now since we have terminals, the nodal voltages V in, v naught dash and v naught, we can use these as the three variables and write the signal flow graph to find the transfer function of this compensation network, that is compensation two-stage op-amp. So that's what we are doing in the next slide. So this is using SFG. We have V in, V naught dash and V naught. So using the expression that is 1 and 2, using the expression 1 and 2, we are writing what is V naught dash is equal to V naught dash is equal to V in multiplied by this plus V naught multiplied by this, and V naught is equal to V naught dash multiplied by this quantity. So which is exactly using the equation 1 and 2. So as you can see now, V naught dash is equal to V in multiplied by minus GM1 by so and so. So we have the same one here, and we have V naught dash given by one more expression, one more term, that is V naught into SCC by G1. So that's what is here, SCC by G1 into so and so. Now this is the expression for V naught dash. Similarly, V naught is given by V naught dash into so and so. So we have this. So you can see now V naught is given by, V naught can be written in terms of V naught dash, that is V naught dash multiplied by this quantity. So that's what we are having there in this. Now since we know the signal flow graph, so we can actually find V naught by V in by writing the power gain and the loop gains. So V naught dash can be written as this multiplied by this. So we have only one forward path, which is this multiplied by this, and we have only one loop. So this is the only loop here. So now this is actually 1 minus of, sorry, this is actually 1 minus, so I would have corrected this, but in the subsequent slides it has been corrected. It's actually, because we have a positive feedback, it's actually 1 minus this product, this into this, because this is the loop gain. So that is SC minus GM2 divided by G1 plus SC2 plus CC. So that's what we have. So once we write the transfer function for this using the signal flow graph, so let us rearrange this. So you can see now in the previous case we have it as minus GM1. So minus GM1, and we have this. Let us take out this minus GM2 outside, and that's what we are doing in the next slide. I'm taking out minus GM2 outside. Now this minus minus will become plus, and we have 1 minus SCC by GM2, and here we are making a slight, of course you can see the denominator of the upper term and the denominator terms are same, so that is going to cancel out. So this is what we'll end up with. Now we can see I have this minus sign, which was actually missing in the previous line. Now this is actually minus. So upon doing this, so let us so we are simply multiplying all the terms over here, and then we are grouping the terms in the next stage. You can see we are simply grouping the terms, and we have taken G1 and G2 common over here. So by taking G1 G2 common here, so we can cancel out some of the terms here. Of course I want all of you to do this once to have a hold on okay what is actually happening. Now finally we can write. Now we can see in the denominator we had actually 1 over G2 and 1 over G1. So this 1 over G2 is nothing but actually R2. 1 over G1 is actually R1. So that's what we are writing here. In the next slide we are writing it as R1 R2. We have actually taken out G1 G2, which was in the denominator, to the numerator as R1 R2. Now this is fine. Now this is taking out the coefficients of S. We are grouping the coefficients of S and A square. So upon doing that, now we can see we have the poles. The original poles were there at P1 dash and P2 dash without compensation. They'll be get moved to P1 and P2, and there is a 0 also coming to picture. Now we know that since there are two poles P1 and P2, the corresponding denominator of V0 by Vn looks exactly like this. So only the denominator, it's actually 1 plus S divided by omega P1 multiplied by 1 plus S by omega P2. This is the location of two poles with new locations omega p1 and omega p2. So let us look into this in the coming video.